every
Sorry. Yes.
hello.
Please. Yes, please. Yeah.
Okay. Like every bounded sequence has a convergence.
Okay, so that is Bolzano Weirstrass theorem for you.
Yeah.
Right. So the statement is, which is very important, every bounded sequence has a convergent subsequence. Right. And this sequence is where?
Of real numbers.
Of real numbers. Okay. Any generalizations? Can you put it in anywhere else?
Okay. In Rn.
In Rn.
Can we?
Okay. Right. Okay, let's put Rn. Arnab, anywhere else is there you can put it?
Actually, it's for real numbers. Maybe I don't know.
Yeah, that is
So
already
theorem
done.
says,
Yeah, for Rn also it is true, right? Same proof will work. But my question is, can we see anything more? So any bounded sequence, so we know what is a metric space.
Yes.
Okay. Arnab, metric space.
yes.
Okay, good. It's good to start doing. So right. So now let us see.
And this theorem will work on metric space.
No, will it work? So let's think. That's my question. But in general, in arbitrary metric space, it should not work. Yeah, every bounded sequence in metric space X has a convergent subsequence. Okay. Then maybe in some metric space, then what can we say about X? Or what examples can we give? Already some standard examples have been given, but yeah, let us think. I mean, if you know any examples of metric spaces, then think apart from the standard ones. What can we say about the metric space X? That is the question. Can we say anything about the metric space?
That X will have a subsequence that will converge to a limit
That is already written.
in that space.
That is already written. Right. But what can we say other than that? That is the question. So do we know what is a compact set in a metric space?
Yes.
Okay. Let's see. Arnab, do you know what is a compact set in a metric space?
Yes, yes.
Okay, then just say it immediately so that we can just go. Yeah. So then we know what is a compact set, right? So then if you know what is a compact set, then you know that K, I'm just writing the definition, K in X is said to be compact if every, and this definition only works for metric spaces. For other spaces, topological spaces and other things, this definition is not, I mean, it's not applicable. Every sequence has a convergent subsequence. Yeah. And one of the key things about compactness is because there are various equivalent conditions which look quite different. And that is what actually make the concept very powerful, right? So, Vaishnavi, what is your definition of compact metric space? I mean, compact subset or whatever.
Given any open cover, we could always able to find a finite subcover.
All right, so that is your that is one definition which you, yeah, maybe I should not say your definition. Yeah, that is your definition. Okay, so these two are actually equivalent. Okay, that every open cover of K. Okay, this yeah, if I need to define, then I will, otherwise I will not. Okay, you have to tell me.
As
Has
a
a,
finite
exactly, right, has a finite subcover. Now, as homework, you should try to prove this, that these two are equivalent, or
I
maybe,
don't know about open cover and subcover.
right, okay, so open cover. So it was very simple. Open cover means covering with open sets. So you know open sets in a metric space, right?
Yes.
Basically any set which is a union of balls. Balls you obviously know. So that's an open. So open cover just means that, so open cover, so what is an open cover? Yeah. So see, I'll define it mathematically, and then you, because intuitively you understand, but there is advantage in defining it mathematically. So an open cover is what? An open cover is a indexed family, like you were reading in Rudin index family. So this those notions are useful in defining these things. So it is an indexed family of open sets, okay, such that union OI. So what is an open cover? First of all, it's an indexed family, right? You may think of it in a certain way, but when you say it, this is a good way to, this is one way to say it. Yeah? Sorry, yeah. Such that this happens, and finite subcover, you understand, means that there is a finite subset, right? Finite subcover means that there exists, has a finite subcover means that there exists a finite subset J a subset of I, right? Cardinality of J is finite, okay, such that union over OJ, this also covers. This is exactly what you expected, nothing surprising, but I just spelled it out, that's all. Okay. Right. So I will erase this. So please try to see or read a proof of this. You will find it in any book, I suppose. Certainly, I believe Bartel and Schobert would have it in some of the later chapters. But yeah, this you can find out and study. It's very fundamental. Okay. but I will erase the second definition. Just keep one definition. And in fact, the first definition is what we will need at the moment. Yeah. But again, as I'll repeat that whenever you meet a concept and you see that there are several equivalent definitions which don't look very obviously equivalent, it means that that concept is something interesting, right? It means that starting to use that concept is going to give you a hold over some interesting collection of objects. So now can you tell me what can you say about this metric space in the language of compact sets? So now if you use this language of compact sets, so earlier when I asked what can you say about the metric space, the question was quite vague. Yes, Arnav.
So we can say that X is sequentially compact.
No, that's not true. And I mean, I did not even say what is sequentially compact, right? They are all same things in metric space. No, but X is not sequentially compact. Is R sequentially compact? No, R is not compact. R has this property. Yeah. But I mean, you're getting there. That's the pin. Basically, this says that this space has a lot of compact subsets. Anyway, anything that we can say? So we can say that every bounded, so we can say about this space, this, I'll just write this P. Okay. Every closed, and see, you need closed. Without closed, you can forget about compactness, right? Yeah. Every closed and bounded set is just don't relate it with X right in the first second. Just first for a second, see this property neutrally. Okay. And then I'm just saying that X satisfies P. Yes. Correct, right? Because if you take a closed and bounded set in this space, right? Take a sequence in that set, and that's a bounded sequence because it's an unbounded set. It will have a convergence subsequence because that's a property of the metric space. And so that convergence subsequence will have a limit, right? But that limit will also be in that compact set because in this set because it's closed. And so you found a convergence subsequence converging inside this set. And so that means it's compact because this is what it means, right? Definition. The limit has to also be in it. That's why we say every sequence has a convergence subsequence in X, convergent in X. Okay, that's important. So this is correct, right? And you very well know this is the property of real numbers, which is very important, right? Very important property of real numbers, or Rn also, right? Every closed and bounded set is compact. Sorry, yeah. Okay, yeah.
You had written every sequence has a convergent subsequence in K.
Yes.
Here,
Yeah. In K, yes. That's why I put the closed condition here. Right?
okay.
Yeah, that's also, it implies it has to be in K. And actually, if I have to express it here, then means initially, then I should write that every sequence in K has a convergent subsequence. And this statement means that it has to converge in K, right? If nothing is said, this statement means that it has to converge in K. Otherwise, it will be like, it's Cauchy or yeah, I mean, if you say convergent subsequence, it means that because I've set the sequences in K. So when I say convergent subsequence, it means it's in K. That's just a logical point, which I'm trying to say that I don't need to write here, I think, that convergent in K. Mathematically speaking, obviously for emphasis, it will be written in some books, may not be written in some books, but right. So it's clear, right?
Yeah,
Now,
like the limit should be in K, like
yes, yes,
convergent.
yes, yeah. Because see, if the limit is not in K, then I will not say that this convergent, that this, yeah, I mean, just, yeah, from the wording, it should be that the limit is in K. You can write it if you want. Yeah, the limit is in K. Right. Yes. Because initially I've said that the sequence is in K, so I don't think I need to say that, like when I say that it has a convergent subsequence, it means that it's convergent in K. Because it's a sequence in K, and so if I say it's convergent, then by default it means convergent in K. But yeah, you're right. I mean, maybe one can write it to be clear. But more importantly, is it clear that this metric spaces have this property? Right? Okay. And of course, I mean, I suppose these two properties are equivalent, right? Basically, I've not done anything so far. That's the point. These are same things. Right? So I'll remove this also and compact something that we understand. So if this is property P and this is property Q, that every bounded sequence, obviously we are in metric spaces, so it's fine, it's understood. Every bounded sequence has a convergent subsequence. So do you see why these two properties are same? So we have proved that Q implies P. Now you want to prove that P implies Q. Right? So you take a sequence in this metric space. Take a sequence x1, x2, xk. It's bounded, right? The sequence is a bounded set. So we want to use right. We want to use P, right? If you want to use P, so what are you given? You're given a sequence, right? You want to prove Q, so you are given a bounded sequence. So you want to make a compact set out of it. So how will you make? So you take this, obviously you would put in these things in your compact set for sure. What else should you put in? Yeah, I mean, this statement actually might be
Can you
wrong.
repeat the question?
Yeah, so we want to prove P implies Q. Where you see what I'm saying. So what I'm saying is that you assume that in your metric space, every closed and bounded set is compact. Okay. And now you just start with a bounded sequence in that metric space. We want to see if it has a convergent subsequence. So now the situation has become opposite. So that is, yeah. Okay. So start with a bounded sequence. So just follow this line. Just follow from here, right? Start with a bounded sequence and see if it has a convergent subsequence. And you are allowed to use P. Instead, you have P. Okay. So let us see. So yeah, I mean, there will be some exceptions, but those will have to do with the definition of some small things, but more otherwise the statement is true. But let's see. So start with S, right? Because what is the goal here? The goal is to construct a compact set. Yes. right? The goal, let me write here, the goal, because you want to use P, how are you going to use P? Yeah. So goal is to construct a compact set. From there, you will find your limit, find your convergence subsequence, right? Once you put something in a compact set, you get a convergence subsequence, right? So construct a compact set. So if I take S to be this, I cannot guarantee this is a compact set. How do I get a compact set? It needs to be closed and bounded. So S is bounded. So maybe I should not even write compact. I should just say construct a closed and bounded set. Construct a closed and bounded set, right? We want to use P. So you take S to be this. S is certainly bounded, no doubt about that. Now, what's the definition of a bounded set in a metric space? I'm not asking. If you're not clear about it, you can just read it. That's a very small thing, so I'm not talking about. But you understand boundedness, but still, you may have to read the definition once. But but again, too many definitions if I talk about, then I won't get to the point. So yeah, S is bounded. But how do you make a closed set? Well, you just take the closure of S. And you don't this is very simple. This is just take S union all limit points of S. Right? Do we know what is limit points of a set?
Yes.
Good. Okay. This is a standard parcel, standard thing that comes with the definitions of metric spaces. You take the limit points of S because you want to make it closed, right? So how do you make something closed? Just take the closure. And what else do you do? This is the simplest thing. Now, the key thing here, which you can feel, I mean, what I'm talking about is if you take a set and then you take its limit points which are very, very close to the set, like that. Yeah. If you take the collection of limit points, the set is changed, but the diameter of the set, which you don't need to know what it is, but I'm saying just that S closure will still be bounded. That is homework. You can prove it. Okay. And if you work these small things out, is how you become. Yeah. S closure is also bounded, and it is closed and everything. So S closure by P is compact by P. By property P, it is compact. So I've not done anything. I mean, I'm just doing the obvious things, right? Just the obvious things. Just take S. I mean, you want to just, yeah. And then we are done, right? Because it's compact, so it has a convergence subsequence. So no, but we are not done. Let's write and then we see. Yeah. So let me just see. I mean, yeah, we are done. So okay, I think somebody said that it is true in every metric space, right? Let me. Yes, yeah, we are done, but this is still, I mean, you have to argue. Okay, you have to argue. So please complete. Okay. Yeah, I mean, I can confirm that it is true, but please complete. Yeah, it is basically it's compact, and so basically you take this sequence in S. S is in S closure, right? And it has a limit point because S is compact, because S closure is compact. So this sequence will have a limit point, right? And that is yeah. I mean, it will have a convergence subsequence. That's the definition. Okay. Yeah. basically, I mean, yeah, you can see it from the open cover definition also, but let's not bring, I think that's not important at the moment. So basically, we are just saying that this set of limit points that you're adding, there is some limit point which you are adding, right? That is the claim. Okay. Yeah. Okay. All right. So please complete this and let me give you a small thing to check. And it's actually very important for several things. X be a compact set. I mean, K be a compact set in X. K be a compact set in X. Then K cannot have an infinite discrete set. And you can look at the definition of discrete. Discrete just means that for every point there is a neighborhood so that it doesn't intersect any other point in the set, right? Yeah, you can look at it. And so as you see, I'm not even defining everything. You can do it, but this is easy. It's very important though. Okay. All right, but see, we have not done anything. That is the thing. And these two properties being equivalent, you can see I'm going around just doing the obvious things. But it's just that the property which we started with, yeah, the property which we started with to study, right? We have sort of made two properties out of it, right? Maybe one of them might be useful. But which metric spaces have this property? Can we say something more about the metric space which has this property? That is the question. Okay. Yeah. So let us think about it. Let us think about it. Let's see. I think if I write another property R, okay, I am willing to write another property R, which is X, and everywhere you can say X, right? Every closed house bounded set in X, this in X. So I'm just, I mean, I can say without X also, but X is locally compact. and don't worry, I mean, I'll describe it. You know, if you don't know, I'll describe it. Just this is a terminology which maybe you have not done. Okay, so but it's a very important concept. We want to now basically, you know, understand these spaces locally from the local nature. And this property is very important in infinite dimensional linear algebra. Maybe I cannot emphasize, so let me not say anything. Let me just give the definition. Definition is very simple, actually. The definition, there are many definitions. I mean, that's the beautiful thing. I mean, this concept is remarkable. This has many definitions. You can say it has a 1-point compactification. You can say you can say many things. So but yeah, but what we need is this definition of this. And when I define it, it is your job to see why it connects with the word locally compact. Okay. Because when you see a definition and then you see that there are many definitions in topology which are of the same kind, locally something, locally that, you should develop the art to extrapolate from the word locally and the definition and the adjective. You should learn to extrapolate the adjective locally in how it is used in this side of mathematics, topology, metric space. Then it will be easy. Because I mean, how do you think I'm remembering all these things? Because I can extrapolate. I mean, to some extent. So anyways, Yeah. So a very simple definition is like this. Okay. So every point P, okay, in X, don't be disheartened by this. This is a very concrete thing. Locally compact is a very concrete thing. Every point P, for every point P in X, just like imagine a point in R2, okay, there exists a sequence of neighborhoods. And this is actually what makes sequences so effective in metric spaces. Okay? There exists a sequence of neighborhoods let me say U, UP1, UP2, UP3, and so on and so on. Okay, descending sequence of neighborhoods. I mean, you understand, like balls of radius. In mind, you just keep open balls of smaller. These are open balls. I'm drawing them like closed balls, but you understand, open balls. Okay, such that P is contained and obviously contained in each of them. That's so the notation suggests, everything suggests that, such that, again, this is not very good way of defining, but otherwise it will become more complicated. So I want to get the idea of that this kind of space can be locally described. And a lot of times to say that something is not this kind of space, the only way you can do it is to prove that this locally is not like this. Because a lot of time you don't know what the space is, you only know what it is locally, like manifolds. Okay, and many things. Yeah, you'll see. So all we are saying is, anyways, all we are saying is that this intersection is just P. So you may just say balls of radius 1 by n and so on. That's all I'm saying. Okay, such that, this is something which always happens in a metric space. As I said, you take balls of radius 1 by n. That's your UPN, right? That always happens. Such that this happens, and all these things are better said as that this is a local base, but not going into that right now. You may not know that. You to see it in the future. It's intersection, you understand, it's just the point. But the main thing is UPI is pre-compact, but that just means is compact. You can extrapolate, not a big deal, right? Property R. Now, can we say that these three are equivalent? Okay. This is what happens in R also, right? You know that closed balls are compact because closed and bounded is compact. So see, what is trivial, what is completely trivial is P implies R. Or yes, right? And P and Q are same. Maybe I'll not write it here. Yeah. P and Q are same, but this implying R is quite trivial. R is the harder property, right? So from there, R is the you understand, right? Saying less in some way, only locally. P and Q imply R is trivial because you just take those 1 by n radius balls, take their closures. They are compact because they are closed and bounded, and by P closed and bounded is compact. So this is done. So that means that these kind of spaces which you are looking at are locally compact. Your all important spaces, locally compact spaces are very important. Yeah. Okay. But the target is to go from R to Q. Okay. R to P and Q somehow, and this is what we will try, and then maybe we will try to we'll go to some problems. So Think about it. Less than a minute is left. After that, as usual, you take some break, 10 minutes break, and then join. Just join and see. The meeting will open anytime the limit is over. So, but keep thinking about this. Right. Your goal is to go from R to this thing. Yeah? If you have a closed and bounded sequence, yeah, you just want to show that it has a convergent subsequence. Right. Yeah.
Hello.
Uh-huh.
You have written